Hi everyone, this is NLP Corgi. Today's deep dive is about the paper from University of Texas at Austin, Inheritune, training smaller, more attentive LLMs by reusing early layers. This work starts from a simple but uncomfortable observation about today's large language models. As we stack more and more transformer layers, a surprising number of the deeper layers stop doing anything interesting. Their attention collapses to almost rank 1, meaning they mostly just copy a single token's information forward. The authors call these lazy layers, and they argue that we're paying a big compute and parameter cost for very little gain. To fix this, they introduce Inheritune, a training recipe that reuses the genuinely useful early layers of a big model to build a smaller model that stays attentive and competitive in performance. Self-attention is the engine that lets transformers connect distant tokens and build rich representations. But when the authors probed real decoder-style LLMs like GPT-2 Medium, Large, and XL, they found that many deeper layers have attention matrices that are almost rank 1. In practice, that means the layer is mostly attending to one position and broadcasting it everywhere, instead of mixing information across tokens. Even worse, the mass of the attention often collapses into a single column, so the layer behaves like a crude copy mechanism rather than a nuanced reasoning step. To make this concrete, the authors analyze several GPT-2 variants: 24-layer medium, 36-layer large, and 48-layer XL. For each layer, they compute the maximum rank across attention heads on real validation data. Early layers show healthy, higher rank attention. But as you move deeper, the rank steadily drops, and many of the last layers are effectively rank 1 across all heads. Those layers aren't learning rich patterns anymore. The paper calls these fully degenerated layers lazy layers because they add parameters and compute without contributing meaningful new structure. Once you see that deeper layers are often lazy, a natural question is, which layers are actually doing the heavy lifting? The authors show that early layers, which maintain higher attention rank, transfer extremely well. If you initialize a smaller model using these early blocks, training converges faster and to better loss than if you use deeper lazy blocks or random weights. In contrast, initializing from lazy layers looks almost the same as random initialization. This suggests that many current LLMs are overbuilt in depth, and that the real representational power is concentrated in the earlier, more attentive blocks. Inheritune turns this insight into a training recipe. You begin with a large, pre-trained reference model. From it, you carve out a smaller target model by copying the first few potent layers. You then train this compact model on your data. After some steps, you expand the target by adding more layers, again, inheriting weights from earlier parts of the reference model, and continue training. You repeat this grow and train cycle until the smaller model's validation loss matches or even surpasses the original reference model, but with significantly fewer layers and parameters. Let's walk through the Inheritune pipeline. Step 1. Pick a large pre-trained decoder-style LLM as your reference. Step 2. Create a smaller target model by copying its first few transformer blocks, including attention and MLP weights. Step 3. Train this target model on your pre-training data for a set number of steps. Step 4. Expand the target by adding more layers, again, inheriting weights from earlier non-lazy parts of the reference, and keep training. You can repeat this multiple rounds. The process ends when the smaller model's validation loss is on par with, or better than, the full reference model. This diagram shows Inheritune in action on a 24-layer GPT-2 medium. The reference model sits at the top. Below it, you see a sequence of smaller target models that gradually grow in depth. The red shading indicates attention rank. Darker means more degenerated, lazy layers. Inheritune deliberately builds the smaller model from the healthier, higher-rank early layers, and only later introduces additional layers as needed. This visual makes clear that we're compressing the model by design, not by pruning after the fact. The authors put Inheritune to the test on several GPT-2 families, Medium, Large, and XL. They pre-train on standard web corpora like Open Web Text and FineWeb EDU. Across these setups, the Inheritune-trained models use significantly fewer layers than the original reference models. Despite this, their validation loss curves converge faster and end up matching, or even slightly beating, the full-sized models. In other words, you can throw away a chunk of depth, keep the good early layers, and still get comparable language modeling quality. How does Inheritune compare to other ways of making models cheaper? The paper benchmarks it against several zero-shot initialization and efficient training techniques, including stacking, hybrid stacking, and half-width models that reduce hidden size. Across GPT-2 medium, large, and XL variants, Inheritune consistently achieves lower pre-training validation loss than these baselines at the same depth. This suggests that simply rearranging or shrinking layers is less effective than deliberately inheriting the most potent early blocks and training them in a staged way. Validation loss is useful, but what about real tasks? The authors evaluate Inheritune-trained models on 5 downstream benchmarks in a zero-shot setting. The smaller Inheritune models not only track the full-sized models in validation loss, they also match their average downstream performance. At the same time, they outperform other models of the same size that were trained from scratch or with alternative initialization schemes. And they reach this performance faster, thanks to better initialization from potent early layers. Another natural baseline is knowledge distillation, where a smaller student model learns to match the logits of a larger teacher. The authors compare Inheritune to logit-based distillation setups, including ones that initialize the student from alternate teacher layers, similar to Distilbert. For both 12-layer and 16-layer GPT-2 medium variants, Inheritune leads to faster convergence and better generalization than these distillation baselines. This highlights that inheriting strong internal representations can be more effective than just mimicking the teacher's output distribution. To understand what really matters in the inheritance step, the authors run ablations on a 16-layer GPT-2 medium. They try initializing different subsets of each transformer block: attention only, MLP only, attention plus MLP, and with or without layer norm weights. The results show that copying attention and MLP weights drives most of the benefit. Initializing layer norms from the reference model has only a small additional effect. In practice, this means that the core computation paths, the attention and feed-forward networks, are what carry the transferable structure. Beyond rank metrics, the authors visualize actual attention maps. In a standard 24-layer GPT-2 medium trained from scratch, deeper layers often show very uniform, unfocused attention patterns, consistent with lazy, degenerated behavior. In contrast, a 16-layer GPT-2 medium trained with Inheritune maintains sharp, structured attention even in its deepest layers. This qualitative difference supports the claim that Inheritune doesn't just compress the model, it preserves and concentrates the genuinely useful attention behavior into a smaller, more attentive network. Finally, the authors revisit the rank analysis to see if Inheritune actually fixes attention degeneration. For the original 24-layer GPT-2 medium, several of the last 12 layers have attention matrices that are effectively rank 1 on average. When they train a 16-layer variant with Inheritune, the maximum rank across heads stays higher across all layers, and none of the later layers collapse to rank 1. So, smaller Inheritune model not only matches performance, it also exhibits healthier, more expressive attention throughout its depth. To check whether this is just a GPT-2 artifact, the authors analyze larger, modern LLMs like OpenLlama 3B, 7B, and 13B, trained on trillions of tokens. They find the same story. As models get deeper and larger, attention mass in later layers concentrates into fewer columns, often with around 90% of the mass in just a handful of positions. Many heads effectively become single column. This shows that rank and mass collapse are widespread phenomena in decoder-style LLMs, reinforcing the motivation for methods like Inheritune. Stepping back, this paper makes 2 main contributions. First, it documents a structural flaw in many deep decoder-style LLMs. A significant fraction of later layers suffer from attention rank collapse and behave like lazy layers. Second, it introduces Inheritune, a simple training recipe that reuses potent early layers from a larger model to build a smaller one that remains attentive and high-performing. Instead of pruning after the fact, Inheritune compresses by design, delivering models that are cheaper, smaller, and yet competitive with their larger counterparts on both pre-training loss and downstream tasks.